Kia ora, my name is Shivam Mansal. This video documents the engineering site inspection of a two-story unreinforced masonry building located at 201 Upper Simon Street, Auckland, New Zealand. This inspection is carried out as a part of the course Civil 745 Seismic Assessment of Existing Buildings at the University of Auckland, New Zealand. The purpose of this inspection is to record and evaluate the architectural and structural features of the building, with a focus on aspects relevant to seismic performance. The site visit was conducted in August 2025, and in this video, I will provide a detailed overview of the building's site conditions, structural elements, facade details, diaphragms, and any potential seismic hazards. This in front of me is the subject building located at Upper Simon Street, Eden Terrace, Auckland. I am standing on Upper Simon Street. To my right, it's the Newton Road, while on the left, it's the Khyber Pass Road. If I go continuously upward to this Upper Simon Street, the road divides into New North Road and Mount Eden Road. And if I go in the opposite direction to the Upper Simon Street, it leads towards the University of Auckland. There are no geological hazards from landslides or neighboring high-rise structures, as there are no taller buildings in the immediate vicinity, nor are there mountains nearby that could pose a landslide risk. The building is located on Upper Simon Street, and since the road slopes downhill towards University of Auckland, the risk of flooding at site is also minimal. Additionally, there is no potential for lateral spreading or liquefaction, and therefore the site is classified as Soil Class C. This is a two-story unreinforced masonry URM building, classified as a row-type structure. Due to this typology, one side of the building is not visible. However, there is a small street behind the property known as Stable Lane, which provides the access to view the rear facade. Although the building is primarily constructed of masonry, the rear elevation has been plastered with concrete, likely to create a smoother finish. It is also important to note that the building is not uniformly two stories across its length. This is a corner view of the building. It is how the building will look like if it was a standalone, like with the last few meters of the building being a one story. As seen in this picture is a kind of side view of the building with some part being one story at the end made as a storeroom for the tenant. Clearing the building's sole purpose was the commercialization of the street. There is no neighboring building taller than this, so estimating there is no likelihood of debris from another building falling into the subject building during any seismic hazard. Since there is no access to the roof, and given that this is a busy commercial area where flying a drone would not be legally permissible, the aerial view has been generated using Google Earth. The image clearly shows that the building has a flat roof with cantilevered gables. These cantilevered gables present a significant seismic hazard as they pose a risk of falling onto pedestrian during an earthquake. At the rear of the building, the masonry walls have plastered with concrete, possibly to provide additional strength, and the finish has been designed to resemble concrete blockwork. However, the door and window on the elevation appear very old and poorly finished, which is consistent with this section of the building being used primarily for storage purposes as mentioned earlier. Majorly, Auckland has soil type C, which is further divided into four primary color codes, that is brown, pink, red, green. The shown picture is developed from GNS Science Geological Web Map application showing the type of soil of site, which is pink, Auckland basalt tuff, Kerikeri volcanic group. The blue mark shows the exact location of the building. This type of soil is formed by volcanic ash and is more than 250,000 years old. Tuff is formed from volcanic ash and debris that settled and compacted during past volcanic eruptions in Auckland. It can vary from soft and weak to reasonable strong depending on the degree of compaction and cementation. often forms the basal layers around the volcanic cones in the Auckland volcanic field, may have limited bearing capacity for the buildings and can sensitive to moisture. All these buildings share common party walls with the internal partition constructed from the timber, while the primary external walls are masonry. Geospatial maps clearly indicate that the buildings are connected by a continuous party wall running from the front to the rear. The individual units are then subdivided internally using timber walls according to their specific design and functional requirement. Overall, the building follow a consistent layout pattern unified by the shared masonry party walls. The ground floor front facade has been extensively modified to create a more attractive and contemporary appearance. It now features a masonry frame finished with a plaster and painted white to suit the current tenant's requirement. With timber frame windows visible on the exterior, from outside the facade appears to be in good condition. However, there is a minor crack visible on the party wall which appears to be limited to the plaster layer rather than extended into underlying masonry and can be therefore be considered negligible. The front facade of the building features several decorative elements. At the top is a cantilevered gable, while the first story is divided into three bays by plastered pilasters that serve a decorative rather than structural function. Each bay contains a window with timber framing set within the wall. A suspended canopy attached to the pilasters provides space for tenants to display their store signage. On the ground floor, the facade is predominantly composed of timber framing and glass, designed to create more open and visually appealing frontage in line with modern commercial use. Both front and rear facades appear to be in good condition. On the front facade, there are no visible signs of weak mortar or loose clay bricks. The rear facade has a smooth, freshly plastered concrete finish, which suggests that plastering was likely carried out to strengthen and reinforce the rear wall. Since going into the building is not possible, it is estimated that the floor and roof systems of this URM building are timber diaphragms. They play a critical role in how these buildings behave under lateral loads such as wind or earthquake shaking. A diaphragm is essentially a horizontal structural element that connects the walls together. In older buildings like this one, the diaphragms are formed by timber joists spanning between the masonry walls with timber floorboards or roof boards nailed on the top. When earthquake strikes, the shaking of ground creates lateral or end-plane forces on the building. The diaphragm's job is to collect these forces and transfer them to vertical resisting elements, which is in this case are brick masonry walls. Without diaphragms, each wall would respond independently to earthquake shaking, making them much more vulnerable to out-of-plane collapse. By tying the walls together, the timber diaphragms help the building act more like a single unit rather than a collection of separate walls. However, there are some important limitations. Timber diaphragms in unreinforced masonry buildings are generally considered flexible, which means they deform significantly under lateral loads. This reduces the ability to shear forces even between walls. In addition, the way timber joists are connected to masonry is critical. In many older buildings, joists were simply pocketed into brickwork without strong anchorage. In an earthquake, this can allow the diaphragm to separate from walls, leaving the facades and parapets unsupported. So while timber diaphragms are essential for structural behavior, their flexibility and poor connections represent a key seismic weakness in historic URM buildings. Since it was not possible to go inside a building, these interior images are generated from current tenant's website, that's Superior Hair Extension. The image shows the interior condition of two-story unreinforced masonry building currently occupied by a hair salon. From the photograph, it is clear that the interior is very well maintained and has been modernized by the tenant to suit commercial use. The flooring is timber, which is consistent with the construction style of URM building from this era. The timber floor forms part of building structural diaphragm, although in this case the actual joists and connections are hidden beneath the polished surface finish. The shop interior has been subdivided by lightweight timber partition walls. In the first view, we can see partition wall separating the shop front from the rear, while another partition divides the main floor into two sections. These partitions are non-structural and have been added by the current tenant for fit-out purposes. Their role is primarily functional to organize the retail space rather than structural, as they do not provide significant lateral strength to the building. The roof is also timber frame, but like the floor, it has been concealed by interior lining and smooth finishes, giving a modern aesthetic. This means the diaphragm features such as joist, anchorage, or cross bracing are not visible in the current fit-out. Another important observation is that external masonry walls have been covered with plywood or lining board. This is a common refurbishment practice to give a clean appearance and to allow shelves and fittings to be mounted. However, this lines also hides the actual condition of brickwork, making it difficult to visually assess cracks, mortar deterioration, or wall anchorage from inside. Finally, it can be seen that the building is divided into two-story at the front and a single-story storage space at the rear, which matches the overall geometry observed from the exterior. The approximately height of the building is 8 meters and the width is around 6 meters. The cantilevered cable, approximately 800 mm in height, lacks adequate support and poses a high significant risk of detachment during a seismic event, potentially falling onto pedestrians below. Providing additional structural support or bracing to this element would reduce the likelihood of failure during an earthquake. The diagram highlights the structural vulnerabilities of these unreinforced masonry buildings. The first and the most important point is that unreinforced masonry walls are weak in tension. Brick and mortar perform well under compression, but when subjected to bending or pulling forces during an earthquake, they crack very easily. This makes them prone to brittle failure. Secondly, URM buildings are constructed from very heavy materials. The large mass of solid brick walls significantly increases the seismic forces that can act on structure. In simple terms, the heavier the building, the greater the earthquake forces it must resist. Another critical weakness is the poor connection between walls and floors. In many older buildings, timber floor joists were simply pocketed into masonry without proper anchorage. During earthquake shaking, these connections can fail, allowing the walls to separate from floors or roof. This can lead to catastrophic collapse of facades and parapets. Finally, the parapets and the decorative ornaments on the top of the URM buildings are particularly dangerous. Without bracing, these elements can topple outwards during shaking, creating falling hazards on street below. Together, these vulnerabilities explain why URM buildings are among the most earthquake-prone structures and why strengthening or retrofitting is essential for safety. Overall, the building appears to be in good condition, especially considering it is more than a century old. However, most of the original structural elements are concealed by modern modification, meaning that the true condition cannot be visually confirmed. Therefore, detailed testing and investigation are essential to validate current assumptions and ensure the structural safety of the building. Thank you.